It's important to understand cloud storage technologies. We're really all storage technologies, and then we can apply that to virtualization in the cloud. So what I want to do in this presentation is go through some of these technologies that are available to us, and later on we'll talk about how we can apply those to data center virtualization and to cloud computing. So as far as cloud storage and provisioning, so like I said, we're going to discuss first how all these different storage technologies work, just what's available out there, what we can use, what's in the toolbox, and then I'll talk about some specifics in the presentation about virtualization in the data center. So there's two different types of access we're going to talk about to files. There's file level access, and then there's block level access. So file level access is when we can access files on the network using some protocol. Usually that protocol is going to be Samba or SMB or server message block. So this would be like a UNC path in Windows. Another possibility would be NFS, which is the network file system. And there's a couple other protocols we can use for this. But here's the distinction that I want to make clear is that file level access, when you have file level access, that means that you have a volume, some volume of storage that is fully managed by an operating system. And for you to access that data, you're going through an operating system which is handling the authentication and is managing that file system. What that means is that many users can access those files in that shared storage device when it's file level access. So there's some management there. You can access the files by multiple different systems. Everyone can read and write to that volume. So that's file level access. And you'll frequently hear file level access. You'll frequently hear the term network area storage or NAS. Or I'm sorry, network attached storage, not network area. We'll get to storage area network in a minute. Network attached storage or a NAS is one of the most common ways to implement this. So when you hear the term NAS, we're talking about file level access, and that NAS is managing access to the files. It's managing the file system. It's managing, it has an operating system. So it's just really a computer. And by the way, you could build your own NAS using pretty much any operating system. You take a Linux machine, you put some storage on it, and you can enable the SMB protocol with some packages in Linux to integrate to Active Directory or something like that. And you've got yourself a NAS, and you've got shared storage on the network that everyone can access. So that's basically what network attached storage is. So here's an example from one of the readings that I gave. This is a picture from the readings that shows kind of what this looks like conceptually. It's very simple though, right? You've got some kind of storage array, and you're accessing it from computers on the network. And by the way, that storage array on the right-hand side would have a computer that controls it. It's got an operating system and all that other stuff we would expect to see in a server, for example. All right, so block level access. So that concludes file level access. Block level access is a little bit different. So block level access is basically when you have to manage the file system. So you have to manage how that binary data is stored on some medium. It could be hard drives, it could be lots of different technologies that I'm going to talk about here throughout the rest of this presentation. So one of the first ways we could do block level access, one of the easiest ways to conceptualize this, and most of us use this, is direct attached storage. This is where we use some technology like ATA, which is IDE, though 1996 called and wants its storage technology back. But that's one. SATA, SAS, Iscuzzy, which is also a very old technology, although it's still out there. See, these are some examples of direct attached storage technologies. In all of those examples, it's think about your laptop. You're probably watching this video on a laptop, or maybe you do some of your coursework on a laptop. And in that laptop, you have a hard drive, and that hard drive is directly attached through the motherboard, into the to the rest of the chipset. So, and there might be some, there's some bus technology that handles that, which would be ATA, serial ATA, or Iscuzzy, and so forth. So that's direct attached storage, and I think that's what most people are familiar with when they talk about storage in computers. So here's an example of direct attached storage. You've got your server, and it's directly connected to these devices using one of these protocols that I just talked about. So dedicated storage is basically when we dedicate some storage space to a particular customer. And so when you hear that term, you're really just saying that it's a dedicated volume that a client can store data onto, or that some infrastructure can use. So we'll talk more about dedicated storage later on. We talk about how cloud providers provision storage. And shared storage is where you share the storage with lots of people. So you're in sort of this shared environment where everyone is sharing the same access to that storage. So you've got dedicated storage and shared storage, and all of them can use these different technologies that we're talking about. So when it comes to block level, so whenever we have, so block level can be direct attached, but if it's not direct attached, then typically we call it a SAN, or a storage area network. There are a couple different protocols and a couple different standards that you can use for storage area networks, and I'll talk about those here. So a storage area network is, now what's different about a storage area network than a network attached storage is network attached storage is where you have an operating system managing that volume and you're accessing it through that operating system. Whereas with a storage area network, you can think of these as hard drives that you're accessing using the network. But you have to manage the file system on that hard drive. So when you connect to that drive over the network, to that storage device over the network, you basically have an empty palette, and you have to manage everything on that drive. You have to manage the file system, how the files are stored, the access to those files. All of that has to be managed by whatever server is connecting to it. It's not common for that to be shared. So it wouldn't be common with a storage area network to have files that everyone on the network can access on a SAN. That doesn't really work that way. What happens at SAN is where we share hard drives. So it's usually an array of hard drives that you can connect to use space on those hard drives that you manage. So you get sort of a chunk of that hard drive space that you have available to you to manage. But you wouldn't really share files in that little chunk. You pretty much own that. If you want to share those files, you would do that as a NAS. So you can turn a SAN can have a NAS front end through which people are accessing that SAN, but typically we don't access the SAN directly. All right, so here's a picture from one of the readings, kind of showing you just a generic picture of a SAN. But let's talk about some of the specifics with storage area networks. So there are three protocols primarily that we look at for SANs. There's Fibre Channel over Ethernet, Fibre Channel, and Iscuzzy. Those are the three primary ones I think that we see most often in data centers. Now, before we could talk about these protocols, whichever of these protocols we're looking at, one thing that's common in the vernacular is the host bus adapter. So typically there's some kind of an adapter that you have to install on a server. So if you want to use Fibre Channel over Ethernet, or Iscuzzy, or Fibre Channel, you have to have some kind of interface to that. So the host bus adapter is the interface to that backplane or to that technology. And I'll talk about what those HBAs are in these different technologies. But let's look at Fibre Channel over Ethernet first. So with Fibre Channel over Ethernet, basically it's fiber, but it uses the Ethernet standards for its transport mechanism. So rather than reinventing the wheel on the transport mechanism between the server and the client, they leverage Ethernet basically, but it's fiber channel technology. So when you look at Fibre Channel, you usually have some Fibre Channel device, and that might connect to a Fibre Channel, a Fibre Channel device might be on the right-hand side here. Using standard Ethernet switches, they interconnect the SAN devices, which are Fibre Channel, to the servers. So this is Fibre Channel over Ethernet. Now Fibre Channel can also be without over Ethernet. So there's traditional Fibre Channel, where we actually use fiber optic cables, and it has its own protocol for communication. So Fibre Channel is another option. You can use this for SANs, but the thing about Fibre Channel that I want to make clear is that you have to have specialized hardware in order to use Fibre Channel. So a Fibre Channel SAN switch is specialized hardware. You can't just use any old Ethernet switch for that. It's dedicated to Fibre Channel. You have to have a Fibre Channel storage controller. You have to have a host bus adapter, which is Fibre Channel. So everything has to be Fibre Channel. It's very fast. It's a little expensive because you have to have these fiber optic cabling all over your data center. But again, it's very fast. It's an older technology, so it's been around for quite some time. So there's a lot of data centers, I think, that still utilize this technology. But by and large, in my opinion, I think what we see the most in data centers today is Iscuzzy. So Iscuzzy, and I guess I should give you a little bit of background on Scuzzy first. So Scuzzy was a a storage technology. It probably goes back about 30 years, maybe actually probably longer than that. But so Scuzzy was basically you had a ribbon cable that had 7 connectors on it in daisy chain, and you could daisy chain Scuzzy devices along that ribbon cable. They could be storage devices, they could be scanners, they could be printers. All kinds of different peripherals could use the Scuzzy protocol. But you can only have 7 of those ribbon cable connections, so you could have up to 7 devices, and it was connected to the ribbon cable, and it was really not unlike ribbon cables you may see in computers today. For example, for a floppy disk, it looked kind of like the same ribbon cable, but a little bit bigger. And if you remember IDE, some of you may remember IDE from the old days. Those were also ribbon cables with the same style connectors on them. Excuse the cough. Um, so Scuzzy, like I said, it's an older technology. It was pretty fast for its time. But what Iscuzzy is instead of using ribbon cables, the Iscuzzy protocol uses Ethernet as its transport mechanism. Now, what that does, because it uses Ethernet, just standard Ethernet cables, it uses the Ethernet protocols, uses IP addresses and all those other things that we talk about with networking. It uses the same networking protocols and protocol stacks that we're familiar with all other areas of networking. So what that means is now, instead of having to mount a storage array over a ribbon cable that has to be in close proximity to a server and only one machine can connect to it, now I can have many different servers connecting to a single storage array using the Iscuzzy protocol, and they can leverage TCP/IP to do that. So they can use TCP/IP to connect to it over the network. So what that means is I can use technology that's already prevalent in IT. I already have Ethernet controllers and Ethernet switches and cabling and all those other things. I already have that in my data center. It's a very well understood technology, and it sort of unshackles us from where our storage has to be located in the data center. We no longer have to have data, storage all over the data center. We can have a centralized storage device, and all of our machines can connect to that centralized storage device for their storage. So you don't even have to have hard drives in your servers anymore if you do this right. You can connect to them directly over the SAN, or to the SAN directly over your network. I will tell you that in a typical data center, so one of the problems with Iscuzzy is it's a tremendous amount of data. So I would caution you that if you're using Iscuzzy, or if you're trying to design an infrastructure with Iscuzzy, you would not want to have, even though it's the same technology as Ethernet and it's the same thing, it uses TCP/IP. Theoretically, you could connect to an Iscuzzy device. You could connect an Iscuzzy device into your standard network, and then you could connect using the same network interface card that's for all the other network traffic to a server. You could use that same connection to mount a SAN, to mount a LUN over an Iscuzzy connection. But it's a lot of data, and sometimes you'll experience high latency and other networking issues when you do that. So the recommended practice is to have a completely isolated, separate network just for storage. So you build a completely separate parallel network for all of the storage related traffic. So it has its own Ethernet switches, it has its own cabling. You would have your own Ethernet LAN adapters or NIC cards, which really is the HBA in this case. The host bus adapter is really just a NIC card. But all of that would be completely separate. And if you want redundancy, you would have to have redundancy for that, just like in any other network architecture. Could you connect to an Iscuzzy device over a wide area network? Well, I suppose it's possible, but it's not generally recommended unless you have a really strong wide area network. But if that network ever goes down, or if you have latency and things like that, it could affect the performance of those servers. So it's good to exercise some caution if you're thinking about doing something like that. But a lot of times when I discuss something like this in reference to the cloud, students will say, "Oh, I get it. Cloud storage is a SAN that I'm connecting to with Iscuzzy over the internet," and that's simply not the case. That's not typical. We'll talk about how cloud storage works later on and how we store in the cloud, and it works a little bit different, but I'll talk about that later on. But try not to get that confused with something like Iscuzzy. Iscuzzy is really a protocol for inside our data center, not so much for external to our data center. So like I said, Iscuzzy is probably the most common data center storage technology as far as how we build SANs and storage area networks and how that works. So that's Iscuzzy. So let's move on. So let's talk about some storage concepts. You have different types of disks. like SSD and spinning disk. Obviously, SSDs are very expensive. Spinning disks are a lot cheaper. Spinning disks generally, they both have failure rates, right? SSD and spinning disk both fail periodically. So we do have to account for that. And I'll talk about how we account for that failure here in just a couple seconds in the next slide. Some of the interface types to those disk types are going to be ATA or IDE. ATA is synonymous to IDE. You have serial ATA, Iscuzzy, SAS, and Fibre channel. Usually SAS we find in enterprise. So SAS is, well, I should go through this. So ATA, serial ATA, Iscuzzy, SAS are all direct attached storage technologies. Fibre channel is direct attached, but it can span much longer distances because it uses fiber optic cabling. So you can have much longer cables, so you're not shackled to being right near the same system. But the other four, SAS, Iscuzzy, SATA, and ATA, are all direct attached. They're typically inside a server. They wouldn't typically be external. The only exception to that might be Iscuzzy, which can be external, but is not really common anymore. That's not commonly used anymore. Like I said, Iscuzzy is really what's used today. So those are our interface types and our disk types. Again, we already talked about direct attached storage, but I just wanted to familiarize you with some of these technologies. So like I said, failure is a really important part of storage. We have to understand failure, that it happens. I always jokingly say that when you look at a hard drive, one of the specifications they give you is the mean time between failure. They give you a bunch of specifications, but what those specifications tell you is pretty much when a hard drive is expected to fail. So they have a finite lifespan, and they are going to fail eventually. And whatever is on that device, we're going to lose when it fails. And I always like to tell students, if you want to know when the drive's going to fail, look at the warranty expiration. It always seems to fail about 3 days after it expires. But one of the ways that we can mitigate that failure is through RAID, or redundant array of inexpensive or independent disks, depending on who you ask. There are various levels of RAID. The ones that I want you to really understand for this class is make sure you're familiar with RAID 0, RAID 1, RAID 5, and RAID 6. I think those will be kind of the most common that we'll talk about in this course as far as storage goes. So one thing that's important to know about RAID 0, however, is that RAID 0 gives us no redundancy. The only advantage to RAID 0, well, let me take a step back. So when we talk about RAID, we're talking about an array of storage devices. So it's not just one disk, it's many disks. RAID would not be applicable if you had a single disk. It's always multiple disks. What RAID 0 is when you have multiple disks and you're using them all at the same time in parallel. So you can write data to all those disks simultaneously, and you can read the data from those disks simultaneously. As you can probably imagine, being able to read and write to all the disks simultaneously in parallel means that you can use that storage array much faster, so you get much faster speeds. So you can take a technology that has speed X, and if you multiply it times 3 drives, now you have X times 3 with the speed. Of course, in reality, it's not that simple, but that's the basic concept. By having more drives that we can use simultaneously, we get better performance. But again, with RAID 0, we have very good performance, but we actually lose reliability and redundancy, because if any one of those drives fails, we lose all of the data in the entire array, because we're not storing all the data in drive 1 and then all the data in drive 2, and then when that fills up, drive 3, and so forth. So they're not like buckets where you fill the first bucket, then the second bucket, then the third bucket. With RAID 0, if you've got 8 bits that you want to store, you store them in each of those buckets one at a time. So those 8 bits get splattered across all of the drives. They're not contiguously stored in one drive. That's how we get that additional speed. That's how we get that better performance, by writing that data and splattering it across all the drives at the same time. So what that means is if any one of those drives fails, our entire storage is compromised. Now, some students will say to me, well, Brian, why is it that if we have more drives, it's more likely to fail? Well, consider this for a moment. Let's say you're in a room with 1,000 people, right? Let's say you're 25 years old. I mean, you guys are probably, most people watching this video are between the ages of 18 and 25. So let's say you're in that age range and you're sitting in a room with 1,000 people. What are the odds that any of those people is going to die before the age of 40? I would say pretty good, right? So statistically, somebody in that room out of 1,000 is probably going to die before age 40. Everyone else will continue on, but one of those people will die. I know it's kind of morbid, but it's a fact of life that death happens, and it's going to happen. So individually, your odds of dying before you're 40 are pretty low, right? Each one of us in that room, out of the 1,000 of us, each one of us has very low odds of dying before 40. Just ask life insurance companies. They will tell you that those odds are extremely low for individuals between the ages of 18 and 25. If there's 1,000 in the room, it's a very low odds that one of those people, that any one of those people are going to die. But the odds that any one of them is going to die out of the entire group is very, very, very high. What if your fate is tied to those other 1,000 people in the room? If any one of those thousands of people died in that room before 40, you also are going to die. Well, now you've got pretty good odds that you're not going to make it to 40 in that room. Because of the way the odds work. And that's what RAID 0 is. If any one of those drives die, it takes the entire RAID array down with it. So we do have a much higher rate of failure with RAID 0 because we have more drives to fail. There's a good chance that one of them is going to prematurely fail before it reaches its end of life. So RAID 0, again, great for performance, not so great for redundancy. So RAID 1 helps us fix that. RAID 1 is mirroring. So with mirroring, all the data that gets stored to disk 0 also gets stored to disk 1. If we had 4 disks, everything on 1 and 2 goes to 3 and 4, and so forth and so on. It's great for redundancy because we have an exact duplicate of our data on another drive. If any one of our drives fails, we can simply replace that drive and rebuild its contents, and we haven't lost any data. So it's a great technology as far as redundancy goes. However, think about efficiency. Number one, if I want to write data to that RAID array, I have to write it 2 times, right? I have to write it once to the first drive and then the second time to the second drive. So write times are significantly slower. To read the data, of course, would be much faster because now I can read from anywhere I want. So I can read in parallel, but I still have to write all that data twice. So I get performance, good performance on read times, not so great on the write times. I do have redundancy, but it's not very efficient redundancy because I have to double my storage space. So for each drive in my RAID array, I have to have a second drive to cover the redundancy. So the more data I need to store, the less efficient this method is because I have to double the number of drives. So that's RAID 1, and that's called mirroring. A good example of mirroring, a good place to use mirroring is typically operating system drives because you only write once, but you read many, right? So you write once, read many. Some people call that worm, right? Write once, read many. The read time is going to be pretty fast, so you're okay there. And operating systems usually have a finite size, so you don't have to worry about data growth, and you can, who cares? You have 2 drives instead of 1. Not a big deal. But for large storage arrays, you would not do RAID 1. You would not do mirroring. It's not common anyway. So the technology that we step to do that is going to be RAID 5. If we want to get better performance on both read and write and more efficiency, we can go to RAID 5. What happens with RAID 5? So imagine you have 3 buckets, and in the first bucket, you drop a 0. In the second bucket, you drop a 1. If you add 0 and 1, you've got an odd number. So in the third bucket, you drop a 1 to indicate that the sum of the bits in 0 in the first and the second drive are odd. That way, if you lose all the bits in one of those 3 buckets, you could always rebuild it by calculating from the parity. You can either recalculate, so if you lose the parity drive, you can recalculate the parity, and you've got your redundancy back. And if you lose anything other than the parity drive, you can rebuild that drive based on the parity. The beauty of this scenario is that if I have 3 buckets and I decide to add a 4th to this schema, I don't have to add any more buckets for parity. 1 bucket still works for the parity. I can have 17 buckets and I still only lose 1 to parity for calculating the whether it's odd or even. So it's much more efficient. The more drives you have, the more efficient it actually becomes. We also still can leverage, just in like RAID 0, I can leverage the parallel read and writes. So I have much faster read and write times than I would if I had single disks, and especially over RAID 1, which is a mirror. If I lose any of those disks, I'm fine. Now here's the problem. What if I lost 2 disks in a RAID 5 array? In that case, you would have lost the entire RAID array. So once again, we do have a problem with failure because if we lose more than 1 disk, we're going to lose the entire RAID array. So to fix that, one method to fix that is to go with RAID 6. RAID 6 is where we have 2 drives for parity instead of just 1. So that gives us an extra drive that can fail. So with RAID 6, we can suffer 2 simultaneously hard drive failures and not lose any of our data. So it gives us a little bit more redundancy, but it's still pretty efficient. So RAID 6 is still a pretty efficient way to store data. So I want to make sure that you're familiar in this class with RAID 0, 1, 5, and 6. The other ones you can certainly take a look at. There's other ones other than the ones that are in the reading. You can go on Wikipedia and read about all these different kinds of RAID. But the most important ones to take away from this class, to make sure you're familiar with in this class, and even in the industry, is 0, 1, 5, and 6. The other ones are interesting, and they're certainly used in the industry, but once you understand 0, 1, 5, and 6, I think you'll understand the other ones much easier as well. So I want to talk about file systems because an important part of storage is file systems. And when we talk about file systems, I want to clarify one thing real quick about the term file system, because even the reading that I gave you kind of mixes up a little bit of this. And I want to make sure that I make it clear that a file system, there's two uses of the term file system. One is how you organize the files in your hard drive, right? In other words, when I say how you organize them, that file structure, the hierarchical structure of a hard drive is the file system in some cases. Some people use that term to describe a file system. Some people use the term file system to describe the actual nuts and bolts and the protocols and the technologies that we use to manage the storage of the binary data on a drive. So this is where we worry about addressing data on a hard drive and how it's organized at a very low level that you and I as a user never see, right? Because this is all stuff that's happening under the hood. Now, the reason I'm telling you this is in the reading they kind of mix this up a little bit. When you look at the reading that I gave you, they have a great explanation of ext. There's various forms of ext, which is a Linux file system and Unix file system. They talk about NTFS, FAT, and VMFS. But when they talk about the Unix file system is not actually a file system. It's a superstructure. It's what I call a superstructure. And you'll see that term if you go Google superstructure or Unix directory superstructure. It's sort of that template of what the structure of a Unix or a Linux or BSD file system should look like, or what the hierarchical structure of the files should look like in a Unix-based system. And the reason that exists, the reason that that's a standard, so if you think about Microsoft Windows, I'm sure a lot of you are familiar with Microsoft Windows. You always have, a drive, or you always have a root in Windows, and under the root you have a Windows directory. You've got a program files directory, and then a users directory, and then inside program files you have all your file folders for all of your programs. Then inside Windows you've got the System32 and WoW64, which has the binaries for the operating system, and so forth and so on. And pretty much any Windows system you look at is going to have the same file structure. Maybe different versions of Windows are a little bit different, but if you're on a Windows XP or Windows 7 or Windows 10, that's all standard. Now, what makes that standard? Who decided that would be standard for Windows? Well, Microsoft did. It's their operating system. They developed it. So they can tell you, they can sort of dictate what that standard is going to look like. Now, take a look at Linux on the other hand. So with the Linux operating system, who's in charge? Well, not really anyone, right? The Linux is an open source product. It's developed by lots of different people. There are many different versions of Linux. If there was 25 of you in a room and I said, what version of Linux do you like? All 25 of you could give me a different answer. You could all give me some other version of Linux. So somebody had to decide what that superstructure is going to look like so we have some consistency, and that's what the Unix file system does for us, the superstructure. The superstructure defines all of the different folders and directories that you see in a Linux-based system or a Unix-based system, and they all pretty much look the same, whether you're using BSD or some flavor of Unix like Solaris, or if you're using a Linux flavor like Ubuntu or Debian or Red Hat or whatever, they all are going to have the same structure, and UFS is what defines that. So I just want to make that clear, that term I call a superstructure, but the reading that you're going to look at calls it a file system, and I think that's a little less accurate to use the term file system to describe that. When we talk about file systems, usually what we're really talking about is that low-level organization of the binary data on the disk. Which again is usually transparent to users and transparent even to system administrators. We might know what that file system is, but I think most people would be hard pressed to tell you exactly how they work. Now, certainly we could tell you what the features are for these different file systems. You should be familiar with the different features and limitations of these file systems. For example, EXT has a couple different versions. There's EXT 2, 3, and 4. What I can tell you about EXT is 3 and 4 are journaling file systems, where EXT2 is not. Some of the limitations have to do with the sizes of the files and how big the volumes can be. So how many terabytes you can use with these different file systems. I mentioned the word journaling. Basically, journaling is where the file system, as it's reading and writing data, keeps some kind of journal as to what's being read and what's being erased from the file system, so that you can replay those in the event of a failure. Non-journaling file systems just kind of make a best effort. So sometimes journaling file systems are a little more impervious to failure if, say, somebody trips over the power cord to the system. A lot of you probably remember in the old days with Linux, if you just turned it off, you would chooch the file system, but that doesn't happen so much with ext3 and 4. And there are other file systems for Linux, but these are probably the most common is ext2, 3, and 4. But I'm sure some of you are thinking of other ones that you've seen in Linux, and they're certainly valid, but I'm not going to discuss them in this presentation, but you could certainly take a look at those. In the Windows world, we primarily use NTFS, which used to stand for the New Technology File System. Which came out with Windows NT all the way back in the 90s. So NTFS is, again, it's a Microsoft file system. Does that mean you can't use it on Linux? Well, yeah, you can. NTFS, I don't want to say it's open source, but it's a well understood file system, and you can use NTFS from other operating systems like BSD and Linux and so forth. So it is available on other platforms. But NTFS is sort of the state of the art in the Windows world. On any modern Windows system, you're going to probably be using NTFS. I think if you're after Windows 7, pretty much only NTFS was supported. They no longer supported FAT32. Speaking of FAT, FAT is an older file system that was developed for MS-DOS by Microsoft. FAT is really not common anymore. FAT32 was sort of the state of the art up to Windows XP for workstations, not for servers. Servers really always they recommended NTFS. But FAT32 does have some limitations, but where we do see FAT32 is in memory sticks and floppy drives, although who uses floppies anymore? But memory sticks is a big one. Could you format a memory stick with NTFS? Sure, of course you can. But usually from the factory they come FAT32. And there are some limitations with FAT32. I think I mentioned in a previous unit that if you try to create a virtual machine with a 60 gig hard drive and it's a single file and it's a fixed size, if you tried to copy that to a memory stick that's formatted FAT32, it's never going to work. You would have to reformat to NTFS and hope that it copies. And I say hope that it copies because sometimes it's hard to copy those large files. They take a really long time, and if there's any little failure, the entire thing fails. That's why it's a little bit easier sometimes when we have lots of files that make up our disks with our virtual machines, as I talked about previously. But speaking of all of these special considerations for virtual machines, another file system that's discussed is VMFS, which is the virtual machine file system, which is developed by VMware. So this is a file system developed by VMware specifically for and optimized for virtualization. When I say it's optimized for virtualization, it has some features and it has some technology that makes it easier to work with virtual machine files. So it is recommended if using VMware to use the VMFS file system. And of course, you can copy a file from a VMFS file system. You could copy it to an NTFS volume if you needed to. So you could go back and forth as long as the VMS, whatever's hosting the VMS file system can connect to the other one. You can certainly do it with SANs and NASs and things like that. So there's always kind of a way to go back and forth. But it is good to be aware of VMFS and what it is. We're almost done here, but I wanted to talk just for a moment about provisioning and creating storage. When I talk about these SANs, one of the things that you'll have to be aware of and that they'll talk about, that you'll hear in the vernacular of SANs is a LUN. And a LUN is a throwback to the old days with Iscuzzy. With Iscuzzy, you would basically, every device had a LUN identifier, and you would mount to a LUN when you wanted to mount a disk or a volume to format it and use it in your system with Iscuzzy. With iSCSI, they use the same vernacular. It's still a LUN. So when you hear the term LUN, really, if let's say you've got a giant SAN that's 100 terabytes, and you divide that SAN up into I don't know, 16 different volumes. Each of those volumes would have a LUN. And you would tell, so if somebody said, hey, I want to use one of those volumes that you created for me on the SAN, they were going to ask you, what's the LUN? So that I can mount to it from with my Iscuzzy driver and connect to it and mount it in Windows or in Linux or what have you. So that's where that term comes from. And you'll see that mentioned in the reading as well. And along with those LUNs, you can do LUN masking and zoning. Whether you're talking about LUN masking or zoning, really what you're talking about is restricting access to those LUNs. So by default with Iscuzzy, all things being equal, if I wanted to mount to a LUN on an Iscuzzy device, all things being equal, if nothing else is layered on top of Iscuzzy, like LUN masking and zoning, I could mount to any LUN I want. So I could, if I know what the LUN number is, and I know what the IP address is of the server, I could put that in my Iscuzzy driver, connect to it, put the LUN number in, mount it, and start using that storage, even if somebody else is already using that storage, which of course is a problem. Imagine if you have two computers trying to manage the same file system and they don't have the concept of clustering. They're going to start stepping on each other's toes. It'd be sort of like having a library with two librarians. One of them likes to use the Library of Congress scheme to organize their books, and the other one likes to use the Dewey Decimal System. They're two completely different systems, and if we're both trying to manage the same library with these different systems, it's gonna screw everything up. We're gonna corrupt our data, which is what happens. So LUN masking and zoning allows us to restrict access to those LUNs. So you can have usernames and passwords so that you can configure who's allowed to access which of these LUNs. Zoning allows you to set up groups of computers that can access groups of LUNs and so forth. So those technologies are pretty important for storage area networks, and especially in our virtualized data centers, which we're going to talk about in another presentation. We'll talk about virtual storage or storage in virtualization with our virtual data centers. And finally, we have multipathing, which is where we don't want to have just one HBA connecting to our storage device. Like anything else, we want redundancy. We're going to talk in much more detail about redundancy later on in another presentation. I'll talk about redundancy and why we use it and some of the things that we can make redundant in cloud and all that sort of thing and what we want to look for in our cloud providers and in our own virtualization. But as far as storage goes, we don't want to have a single point of failure for anything. So we talked about using RAID to make sure we don't have a single point of failure on the drive. But what good is that if we have a single point of failure in the controller that's accessing that RAID or accessing that storage device? So multipathing gives us multiple paths to a single storage device. So instead of having a single interface, so imagine that serial ATA device inside your laptop. You know, there's one cable. You plug in one connector to a hard drive, and that one connector connects to the motherboard or to the controller for the serial ATA device if you're looking inside your laptop. And if that fails, you know, if you took a pair of cutters and you cut those wires, you will lose access to the hard drive. But imagine if you had two connectors on that hard drive and you can connect it twice to your motherboard. Now you're protected from a failure. Now the controller still would be one controller, but what if you had two completely separate controllers, and each one connected independently to the drive? And that's what multipathing is. And that's typically done with SANs, with Iscuzzy and Fibre channel and so forth. Most of those technologies support multipathing. In fact, with SANs, multipathing is supported natively with Iscuzzy. So hopefully I've level set everyone on storage technologies, and we have another presentation in this unit where we're going to look at virtualization in the data center, and not just virtualizing our servers, but also the virtual networks and virtual storage where everything is virtualized. So we'll talk about that next.